morning, everyone. My name is Siddharth Yadav. Currently, I have joined as a PhD scholar in IIT Bombay. Today, I will be presenting my work based on Toolkit for radar analysis and classification for education. I am working under guidance of Professor Hindu in Civil Engineering Department, IIT Bombay. So, starting with my outlines, I will be going through the introduction, working principles of radar, the wavelengths used in India, the polarization and different moments used to calculate the types of precipitation, some problem statements, methodology, results of the trace toolkit, and its utility by using the terrace DWR data. And through this, I'll be presenting some demo of my work and the way forward. So starting with some basics of radar metrology, as it is very important for weather surveillance and disaster preparedness. So we have to use these DWRs for to provide better measurements of rainfall intensity and the velocity by using Doppler effect. So these instruments are vital for monitoring and analysis and analyzing the wind fields and monitoring the extreme weather events. So as per Indian scenario, right now the expanse of the DWR network is 39 stations have been installed in several places across the country, and the future target is to install the 73 DWR by 2025 and 26, and further it will be increased to 126 by 2026. So the scope of this work is tremendous, and for this we need some advanced and indigenous analysis and then some training platforms. So as we know, some basic principles of radar, that it operates by transmitting electromagnetic pulses, and the pulses travel to the object and are reflected back. So the reflected back pulses are called as a backscatter. So the received pulses are of our interest, and a small fraction of reflected energy is returned, and we analyze the atmospheric events based on this. So in radars, in India, we are using three different band radar systems, that is S band, C band, and X band. So the wavelengths, as we can see, the S band has a greater wavelength, that is 10 centimeter, and C band with 6 centimeter, and X band with 3 centimeter. So the use of these different bands based on our requirement. The S band is predominantly used for a ground installation for cyclone detection. C and X band are more used for a better spatial resolution, that is for in Himalayan region for cloudburst situations. So by using these wavelengths, two polarizations have been used, like single polarization and dual polarization. Earlier we used to use single polarization. Through single polarization we get reflectivity, radial velocity of wind towards the radar system and away from the radar system, and the spectral width, which calculates the turbulence within the atmosphere. After the advancement of polarimetry, the dual polarization came into picture. So from there we used to calculate the differential reflectivity, which also tells us the shape and the type of the target, whether it's a rain grapple or what size of the rain drops are being occurred. The correlation coefficient, which tells the uniformity within the space sample, and the differential phase. So the problem statement which tends to develop this trace toolkit was, first thing is, as per visualization, we don't have something called as better simulation platform which tells us the complex radar geometry, what physics is being involved in the beam and propagation concepts. Large and complex net CDF radar data sets has not been analyzed, and the absence of a single interactive and user friendly platform was missing. So for this, we proposed one solution called as a TRACE, Toolkit for Radar Analysis and Classification for Education. So as it is for both the education purpose and the research purpose. So basically it contains two components. One is the education part, where the young researchers or the young fellow will be learning about the basics and the simulation part. And the second part involves the research component. So the toolkit has been developed by using few of the libraries. I have used Python, using the custom tkinter framework, and using some key libraries to build some of the concepts, which is like radar range calculator, antenna radiation pattern, some geometry simulations, reflectivity simulations as well. And to test my toolkit, assess the utility, I have used the Terrell's DWR data and extracted some of the variables, which I will be showing in further slides. So the results, from those results, we'll getting the conceptual clarity for the geometry, propagation, and the antenna characteristics. Also, we will be classifying the hydrometeors, which is used for educators and researchers, and which promotes the hands-on and scalable geospatial learning. And this is the dashboard of my toolkit. So the first which I told about, the built-in radar range calculator. So in this we are using the parameters, that is the transmitted power and antenna gain, which is used to have a better directivity towards the target, radar cross section, and the minimum detectable signal. By using these parameters, we can get the range, maximum detection range through which we can see the target. And the next is the antenna radiation pattern. So by using the power transmission and the gain, we get to know the directivity and how the antenna gain will benefit to calculate the effective radiated power. And these are the interactive tools by which we can play with the values of the gain and the power. Simulation, radar simulation. This basically helps us to understand the two concepts of plan position indicator and the constant altitude PPI. So as we know, the antenna moves in the azimuth direction from 0 to 360. So at different elevations, when we have a scanning of the atmosphere, so at different elevation we get through the volume scan in the vertical direction. So they are basically two concepts. The 360 rotation at different angles is called as the plan position indicator, and once we are fixing the azimuth at certain direction and moving the elevation angle, we get to know the constant altitude PPI, which helps us to understand the vertical structure of the atmosphere, which is aloft in the vertical geometry. So the reflectivity simulation helps us to understand the values which are being the reflectivity values which we get directly. So it is not just like we are getting into drop by drop, right? So there are some range bins are there. So in those range bins, the value of reflectivity is being counted, and those range bins gives certain values, which we call it as a reflectivity, and it depends upon the number of drop counts, how intense the rainfall is. So as we can see, there are 6 bins and showing the different values. So this was one of the simulation I tried to like simulate by using few of the targets as drone, birds, plane, and the hailstone, just like mimicking the atmospheric situation. So this we can see in demo also, and these are the location. This is the location shown by a red dot in the map area, and these are the range bins placed. So this is the 2D structure which I showed you, and this is the 3D structure. Like wherever the the drone or the other targets are being monitored, it will be showing the detected portion, and also I can export in the CSV file to know the where the particle has been detected and at what time and which place. So the utility of trace has been checked by using the Terrell's data from Thiruvananthapuram, and this has been used to check the different variables which can be extracted from the NC file. So few of the variables can be extracted from by using this toolkit. So the first one is the plant position indicator, which the first one is the plant position indicator. So through this we get to know the reflectivity as shown earlier, and the radial velocity. So the patches which we see is basically the center point is the radar, and around it the different parameters are being extracted: the radial velocity, spectral width, and differential reflectivity, and differential phase, and correlation ratio. So it shows that as we see for correlation ratio, it shows the uniformity in the atmosphere. The more the value, the range lies between 0 to 1. As the value tends to 1, the more the uniform the atmosphere is. And the second parameter which we variable extracted is the volume coverage pattern at different angles. There is 0.5, 1, and 2. So it shows that as we increase the elevation angle, we tend to lose some of the data beneath it. So it shows the different range and the height relationship. The 2-degree sample samples higher atmospheric region at shorter ranges and tend some data beneath it. The next is the echo classification. The echo classification is basically based on the classifying the targets into meteorological and non-meteorological data. Non-meteorological means whether it is a dust or some non-meteorology, like some insect, some unwanted targets which are not related to meteorology. As we can see, the I have shown you for elevation at 2 degree. So the left panel shows us the patches of blue, patches of yellow, which is meteorological data, and the black one is the non-meteorological data. And the right panel shows the data which has been classified into different types of the precipitation, whether it is a cloud, light rain, like showers are there, heavy rain, and some extreme rainfall has been occurred. So I would like to show this demo video. Not getting this. Yes, sir. Sir, this was I was talking about the at different azimuth direction we get to have a PPI, the plan position indicator, and if the azimuth is as certain angle from the north, it to have a CAPI like constant altitude PPI. Yes, sir. Yes, sir. Yes. So like at like this toolkit is like we are further planning to uh, like develop into a like one-stop solution for beginners and the research both, and some additional data source has to be tested. At this was the NC file which has like been used, and some other files has to be tested on the same platform, and the few more concepts has to be added to expand the visualization part, and the like we are encouraging some community contributions for this in ecosystem, and no, thank you so much.
Thank you so much for this